All right, today we're going to finish up the oceans chapter. It shouldn't take too long. We got a pen. Success. All right, so this is where we left off yesterday. Where we finished yesterday was your passive margins and breaking down the different parts of the continental uh, the continental. Well, there's the shelf, the rise, and the slope. And my brain's missing the continental margin. There it is. So we have the shelf, which is relatively flat, the slope, which is very steeply inclined, and then the rise, which gently drops down until you get to your deep sea basin or your abyssal plain. And so this is what you would see in a passive continental margin, where your oceanic plate and your continental plate aren't really moving relative to each other. There's no subduction, there's no separation going on. It's just a standard plate boundary that is inactive or passive. So they have a map here that is kind of introducing the active continental margins, where you have subduction happening of your oceanic plate being subducted underneath your continental plate, which is going to have a slightly different profile. So your active continental margins, the main difference here is you're going to have a deep ocean trench where your plate is being subducted underneath, and it kind of pulls your continental plate down with it and creates a very deep trench, a la the Marianas Trench near Japan. As that happens, your oceanic plate can have a lot of sediment kind of scraped off, like mud being scraped off of your boot, and that can form an accretionary wedge. So all that sediment just gets built up in that trench as everything gets scraped underneath, and that can kind of form a new little landmass of its own. Some subduction zones don't have a lot of sediment, so you don't build up a very big accretionary wedge. This is actually not a subduction zone or an active margin. It's just another picture of your submarine fans. So this would be a submarine canyon coming off of your continental shelf down the slope, and the rocks that they form here as your underwater landslides happen are called turbidites. They all get mixed up like your turbulent current, and so we call them turbidites or turbidity currents. So here is an example of your active continental margin, where you have everything your oceanic crust being subducted underneath your continental crust. It kind of pulls the edge of the continental crust down, and you get this really deep trench that happens anywhere you have oceanic crust being subducted. They show you the accretionary wedge, so you can see the thin layer of sediments on the oceanic plate, and as it goes underneath the continental plate, there's contact there, and so that loose sediment gets scraped off, just like mud on your boot. If there's not a lot of sediment, there's not going to be a very big accretionary wedge built up, and you can get a very deep trench, deeper than your standard trench where you do have a lot of sediment. It kind of fills in the gaps there. Okay, so describe the differences between active and passive continental margins and where is each type found. Your passive margins don't have any activity. I mean, it's kind of right in the name. There's nothing going on. The continental and the oceanic plates don't move relative to another. They're just kind of hooked together and stay together. Your active margins, you do have subduction happening. You have some sort of movement. You're going to have more volcanoes, more earthquakes. You're also going to have accretionary wedges as all that sediment gets scraped off. And so they're going to have a slightly different profile. Many of them will still have that continental shelf, but what happens beyond the continental shelf is a little bit. I mean, it's subject to change depending on what kind of plate boundary you have and where you're at in the world. So now, deep ocean trenches. So they're going to go in specifically and look at deep ocean trenches. They're going to run the entire length of that plate boundary where you have oceanic plate being subducted underneath continental plate. So they're going to be long, relatively narrow features. They're not very wide. They are going to be the deepest parts of the ocean. The deepest part that we know of to date is in the Marianas Trench, and has only been explored in limited capacity, just due to the depths and the pressure and the amount of money it costs to get down there. Most are located in the Pacific Ocean because that's where most of the subduction zones are at. They are located as subduction zones and associated with volcanic activity, volcanic island arcs, and volcanic continental arcs. And so Japan is a volcanic island arc, so the Marianas Trench is pretty close to Japan. Now, out in the deep ocean, we have a couple features that we're going to talk about. The abyssal plain is your deep ocean. So if you ever think of, I don't know where, I would guess that the Titanic sank in the abyssal plain. But you're very deep ocean where you get down and there's no light, there's no wave action happening. There's very little life. There's life. There's more life than you would expect. But compared to the surface or the continental margins, very little life comparatively. So likely the most level and flat places on Earth, sites of a thick accumulations of sediment because of all the life in the water column above it, raining down its detritus. And abyssal plains are found pretty much anywhere there's oceanic crust. Now, kind of sprinkled throughout the deep ocean basins and the abyssal plains, you're going to have little mountain features from volcanoes called seamounts or guyots. Seamounts are going to be underwater volcanoes that never reach the surface. Guyots are going to be underwater volcanoes that did reach the surface but got eroded off in a flat manner, so almost like an underwater plateau in a way. And they may show a picture of that in a second. So they may emerge as islands. They may sink and form flat-top seamounts called guyots or table mounts. And no, they don't have one. This does show us a seismic feature. So this is what the actual seismic looks like. When we take ocean seismic, did I say that? Yeah, we talked about bathymetry in the last class. And so you have a boat, you have your receiver. We did used to use explosives. We'd literally just drop like an explosive out the side of the boat. When it explodes, it creates a shock wave. That shock wave goes down, and yes, it bounces off of the ocean surface, but it also has enough energy to transfer through down to the lower down layers, where at each layer boundary, it will also reflect back up. And if you have a receiver that's sensitive enough and knows what to look for, you can receive those signals as well. And so you pass it through a computer and some software that can interpret it, and you get a seismic readout that looks very similar to this. Now, it's not going to be perfect. It's not going to be labeled for you. There are going to be artifacts that you kind of have to interpret. But you can see the overall similarities between this geologist sketch interpreting the seismic and the seismic itself. You can see this peak they have right here. That's interpreted as a volcanic peak. You can see some dips in the layers down here. That was probably an underwater like canyon or a depression feature that has been filled up with sediments over time. You can see that the seafloor is relatively flat, minus that little peak that's sticking up just above the seafloor here. And so there's lots of features here. There's some interpretation that needs to be done, but this is pretty interesting work. This is what I went to do my master's in. So now they move on to Mid-Ocean Ridge. It's an interconnected ridge system, the longest topographic feature on the Earth's surface. Specifically, the Mid-Atlantic Ridge is the longest one. If you include all of them, it gets even longer, but they're not all connected. So over 70,000 kilometers or 43,000 miles in length. They cover about 23% of the Earth's surface, and they wind through all the major oceans. There's every ocean, even the Pacific Ocean, has some sort of spreading ridge somewhere in it. Along the axis of some of the segments are deep down-faulted structures called rift valleys, and we've talked about the rift valleys before. Basically, there is a ridge all along where your spreading is happening, but right at the very center of that ridge, you have your actual rift where everything's being pulled apart and a nice deep valley there. So you can see in the Atlantic, you have a giant one that runs all the way pretty much from the Northern Ocean down to the Southern Ocean. In the Pacific, even though you have subduction happening all the way around the Pacific, there is a ridge in the middle of the Pacific here, not too far from the Galapagos Islands, which also has its own little spreading center there. There's one down here in the Southern Ocean and the Indian Ocean. They're pretty much everywhere. Anywhere you have subduction, you also have to have an equal amount of spreading centers, or else the Earth would be getting larger or smaller, depending on which one you had more of. So they're just showing you also some of the speeds here. They're telling you the mid-Atlantic spreading center is very slow. The Pacific one is going to be very fast, and then your southern ones down here are going to be like intermediate, somewhat like a middle speed going on. This is just another picture of the ocean ridge, so you can see the entire ridge system, which is pretty much the entire picture here. And then right in the center where everything's actually pulling apart, you have your Rift Valley, where you have that nice depression there. And that's just a zoom in of the overall mid-Atlantic ridge they have there. So ocean ridges are characterized by what? An elevated position. So that's going to be your actual ridge itself. Extensive faulting, both divergent faulting and transform faulting to kind of offset the snake-like features in the mid-Atlantic ridge. Lots of volcanoes. They're not big explosive volcanoes. They're just a gentle kind of erupting as your cracks open up. Magma comes up and fills the surface. They don't ever get super big. They don't ever really crest the ocean surface. They just stay below ground. A consistent layer upon layer of faulted and uplifted basaltic rocks. And the Mid-Atlantic Ridge has been studied more thoroughly than any other ridge system, probably just because of all the travel back and forth between the United States and South America and Europe and Africa. That's a pretty heavily traveled area there. So, although oceanic ridges can be as tall as some mountains on the continents, list some ways that oceanic ridges are different. So it's the type of plate boundary. Continental mountains are going to be conversion plate boundaries, where your mid-ocean ridges are going to be divergent. The type of volcanism, continental volcanism is going to be more explosive. It's going to be more felsic and granitic, so your lighter colored rocks that have more silica. On your mid-ocean ridges, they're going to be more gentle volcanoes, underwater volcanoes, much smaller, and have a basaltic type composition with more iron and magnesium, dark colored rocks. And then the type of tectonic stress resulting features, that's pretty much the same as the plate boundaries. Compression on the mountains as everything collides, and then tension in the oceans as everything kind of pulls apart in your divergent plate boundaries. So seafloor sediments, they're going to talk about seafloor sediments and how they build up a little bit. Your sources for your seafloor sediments are going to be turbidity currents, which are going to bring the sediments from on land or on the continental shelf down into your deep ocean areas, or sediment that slowly settles to the bottom from above. And what they're talking about here is from living things in the ocean column, all the tiny little plankton and little fish and all sorts of other small organisms. When they die, if they have any hard parts, or even if they don't, their bodies settle down to the bottom of the ocean and just kind of pile up on the ocean floor. The thickness does vary, depends on how much life, depends on how close you are to a continent. Thickness in the trenches is up to 10 kilometers. In the Pacific Ocean, you have 600 meters or less because you have a lot of subduction going on there. The plates aren't super old. The Atlantic Ocean, depending on what part, because it's a spreading center, you have 500 meters to close to 1,000 meters, depending on how old it is and how much time it's had for the sediment to build up. And mud is the most common sediment on the deep ocean floor. It's going to be different in composition, but pretty similar to the mud that you feel at the bottom of a lake. That nice soft mud. That's you know what I'm talking about. The soft lake mud. It's very soft, very soft. So types of seafloor sediments. Just a side note. Speaking of soft, my 8th period class has been passing around notes. I've just been like hesitant to like grab one and be like, let me see what your note says. They probably shouldn't be passing around notes, but yesterday, like, they forced the issue because they brought it up in front of me. They were like, we're passing around notes, like daring me to look at it. So yeah, I grabbed it and looked at it, and literally it was just a piece of paper that had George Strait written on it and like a George Strait song, which is the weirdest thing ever. But the paper was so soft, it felt like a piece of cloth. Like they had rolled it up and unrolled it like 100 different times. It didn't even feel like paper anymore. It was the weirdest thing ever. My eighth period is a very weird class. So, good thing is, no one will ever watch this video and tell them about it. Sorry, got off topic for a second. Back on topic. Types of C4 sediments. We have two different types, I believe. I'll have to see where they go with this. But terrigenous, think of the word terrain. Terrigenous is going to be from on land. Terrigenous sediments, material from weathered continental rocks. Virtually every part of the ocean receives it. Even if you're really far away from the continents themselves, those tiny little particles remain suspended in the water for quite some time and can move very far distances. Oxidation often produces red and brown colored sediments because it has some sort of iron or metal that can rust in there, and so that happens in the water. And then you have your biogenous, I believe is how that's pronounced, biogenous sediments, which are going to be your skeletons and shells of marine organisms. Like I said, the things that live in the water column, as they live and die, their bodies and their detritus are going to fall down to the bottom of the ocean floor and kind of just pile up there. These are most common in calcareous oozes. A calcareous ooze sounds weird. It's basically a bunch of small microscopic shells and skeletons of little bitty organisms in the water column. If you think of like the chalk cliffs that we saw a picture of, that it's just like built up white chalk. That's all a bunch of little microscopic skeletons and shells of little organisms. And before it gets solidified into a rock, it's just like a mud, but it's like a white mud, very soft. That's the kind of stuff that's going to end up being the limestone that is so prevalent here in Texas. So, siliceous oozes are also another thing, composed of skeletons of diatoms and radiolarians. These are a little bit different. These are still very microscopic, but instead of using calcite or a calcite-based mineral to build their skeletons, they use quartz-based minerals, so silicate-rich to kind of build their inner structures. And then you also have a phosphate-rich material derived from bones, teeth, and fish scales. Not quite as prevalent as the calcareous or the silicate, but it does happen. They don't show a picture of diatoms and radiolarians. I will show you a picture of one. There it is. Thank God. I don't have to look it up. But diatoms and radiolarians are super awesome. They're incredibly varied. They're incredibly intricately structured. Like this one definitely looks like something like designed. It doesn't look like a thing that would just naturally exist in microscopic things in the ocean. It's got different parts. There's a lot of them, they say, that look like hat boxes. They're circular but flat on the top and bottom. They have these nice kind of symmetrically holy textures in them, and they are extremely varied. They're everywhere in all the water column, especially in the oceans, and you could spend probably like a lifetime studying them. They're pretty interesting. Hydrogenous sediments. So hydrogenous sediments are minerals that precipitate directly from seawater. Most common types include manganese nodules, calcium carbonates, metal sulfides, and then evaporites. I don't know that I've ever seen a manganese nodule, but calcium carbonates and metal sulfides are pretty common. And then evaporites are going to happen whenever you have a body of water that has a lot of dissolved minerals in it, and then ultimately that body of water dries up. And when it dries up, all the dissolved minerals stay behind and your water leaves, and you get something like the salt flats. I guess this would be a manganese nodule. So basically, you have metal like dissolved into your water, and then you're probably getting your influx of metal from around here in your smokestacks. I mentioned these yesterday, the undersea smokestacks that are there. I don't know if this would be something that kind of forms right near the smokestack, or if near this smokestack in a highly metal enriched water, you would get these kind of squeezed out as the sediments themselves get pressed and kind of compacted. I don't know. Thank you. And then distribution of your seafloor sediments. Your coarse sediments are going to be terrigenous deposits that dominate the continental margins, just simply because the bigger your pieces are, the harder it's going to be for them to travel far out into the ocean basin. You'd need a strong current to take them there, and usually that kind of dies off pretty close to the continental margin. Your fine stuff is going to be pretty much everywhere. It can go all the way out into the deeper ocean basins. It can also fall out right by the continent. It's going to be much more widespread. Your hydrogenous sediment comprises only a small portion of deposits in the ocean. So these are like your metal nodules or your evaporates or also other things like that. And then few places where very little sediment accumulates are going to be like your mid-ocean ridges. And that's only because that land there is literally brand new. It just got created by the mid-ocean ridge, so it hasn't had time to fully form. So the seafloor sediments are a storehouse of climate data. We will talk a little bit about this more next semester. But organisms record climate data become part of the sedimentary record. And what they mean by this, so think of like an organism that has its shell. When it's born, it doesn't have a shell. It has to kind of grow its own shell. And so what it does is it pulls minerals out of the water column in a natural process and builds its shell around it. Not physically, but chemically. In the same way that your body eats and drinks food and then creates fingernails out of that to protect your fingers. Ocean organisms eat and drink and process all the things they need to survive, and then their body has the chemicals in it to create the shell around them as they grow and get bigger. And that shell kind of records what stuff they have and what stuff they don't have. I don't know if y'all have ever heard of this, but if you're malnourished, if you're not getting the right kind of vitamins, your fingernails will get different things in them to kind of indicate that. Like you'll get ridges or they'll be discolored. It's kind of the same thing with ocean creatures. If there's a whole bunch of CO2 dissolved in the water because there's a whole bunch of CO2 in the atmosphere, that will show up in their shells. It's probably more difficult to kind of suss out and do the research on, but there's a lot of research that does this. It's a good record of what's been happening. So it records temperature changes revealed in the sediment cores from the ocean floor, and there's a lot of different data that you can get, not just from the organisms, but from the rocks themselves. Wonderful. So at the very end, list and describe the three basic types of seafloor sediments. Terrigenous is going to come from your terrain. Biogenous is going to come from your living things, skeletons, shells. And then hydrogenous are going to be minerals that are precipitated from the water column directly. So, nice. And we are done. Wonderful, wonderful. That's it for today. We will... I think we'll start the next chapter tomorrow. I'm going to have your homeworks up today, so I'll send out an email to everybody reminding them of that. Have a nice day, Ian. If you do watch this, send me an email and be like, stop questioning whether I watch the videos or not.